Hi, welcome back. We're up to Lecture 6, Segment 3. The topic of this lecture is measurement, and the topic of this specific segment is the importance of sampling. So, in this segment, we're going to talk about the importance of random and representative sampling. We talked about this back in the first week when we talked about descriptive statistics, but I want to emphasize this again in relationship to measurement issues and with respect to evaluating correlations. So the important concepts and topics to take away from this segment are first just this idea of random and representative sampling, the concept of sampling error, and the concept of standard error, which is a measurement that we're going to use throughout the rest of the course and is critical for understanding inferential statistics, which is what we'll start launching into in the next lecture. So first, let's go back to the color wheel illustration from Lecture 1, where I demonstrated this idea of randomness. So again, assume we have this color wheel and we can spin it, we could play a game, we could make bets on the wheel landing on certain colors. If it's a fair game, we're assuming that the likelihood that the wheel lands on any color is equal. So the likelihood of landing on the blue slice is equal to the likelihood of landing on the red slice, and so on. So if I spin the wheel many, many times, then I should get the same number, approximately the same number of blues as reds, as yellows, and so on. So we demonstrated this in Lecture 1. If we plotted the outcomes in a histogram, then if it was truly random, so if it was a fair game, right, if it wasn't rigged, we should get a histogram that looks something like this. So it should be approximately the same number for each color. And again, from Lecture 1, we saw an example of a rigged wheel. So this wheel was rigged to land on green much more often than, say, red. Okay, so this is an illustration of a non-random process in that color wheel example. Now let's apply that to sampling. Remember, sampling is the idea that we want to do research, and we want to do research that makes generalizations or tests hypotheses about a large population, but typically we can't get our hands on everyone in the population, so we try to get a random and representative sample. Of course, we can't get the entire population, so we're always going to be dealing with this issue of sampling error. And sampling error, defined, is simply the difference between the population and the sample. So if you look back, if we go back just 2 slides, this was a truly random process. We generated this in R, and it was truly random. Yet you notice it's not perfectly equal in terms of how often we landed on yellow or how often we landed on green. There's still some sampling error. So even our random process isn't perfectly random. There's some fluctuation just due to chance. That's sampling error. In statistics and in inferential statistics, which is what we'll be doing going forward for the rest of the course, the main problem here is that we don't know the population parameters, right? That's why we're getting the sample and trying to do this inference. So if sampling error is defined as the difference between the sample statistics and the population parameters, how can we calculate that if we don't know the population parameters? Well, we can't calculate it exactly, but we can estimate sampling error. So how do we estimate sampling error? Sampling error mainly depends on the size of the sample, and that should just be intuitive, right? If I'm trying to make a generalization about all healthy young adults or all healthy children, and I only sample, say, 10 from the Princeton community, that's not a very random or representative sample. There's likely to be very large sampling error. In contrast, if I go out and I get a global sample, say I do this online, and I get a global sample of 10,000 people, then I'm much more likely to approximate the population parameters, and I'll have very small sampling error. So very simple idea. The biggest thing that influences sampling error is sample size. And that should be intuitive conceptually, and mathematically you'll see it's very easy. Also though, note down below that sampling error also depends on the variance in the population. Again, we typically don't know what the variance in the population is, the exact value, but again, think if there's a lot of variance in my population, then I'm likely to have more sampling error. If there's very little variance in the population, then it doesn't really matter who I sample, right? So as variance in the population increases, sampling error is also going to increase. So to illustrate this, again, using the color wheel illustration, assume we have 6 different samples, and these 6 samples just differ in terms of sample size. So we'll go from a small sample of just 10 individuals up to a large sample of 1,000 individuals. So if we did that, and we plotted them in terms of this color wheel illustration, what you see is the distributions get more and more representative as we increase the sample size. Again, this should be intuitive, but I really like this illustration because you can just see it right here in these 6 graphs. And again, this was just generated randomly in R. So if you look at the first one, which has a very small sample, there's only 10 individuals in that sample, we get a lot more purple, or maroon if you will, than we do, say, yellow. There's actually no yellow represented in that sample. But as you go to this very large sample of 1,000, we have almost equal frequencies of all colors. So it's a truly random and representative sample. I could also illustrate this in histograms. So what will be important for us going forward is as we get larger samples and we minimize that sampling error, we're going to get more and more normal distributions, which is great because a normal distribution is one of the underlying assumptions of a lot of the statistical procedures that we'll be covering moving forward in this course. So here what I've done is just plotted these, again, these 6 different samples, but I've plotted them to see how closely they approximate a normal distribution. And if you look closely, you'll see this smooth curve here. That's the normal distribution. And it's very easy to see that with a sample of just 10 subjects, I'm not getting a very normal distribution. It looks like, you know, there's a slight negative skew in there. The mode, it looks much higher than the mean. But then if we go again to this really large sample, it's almost perfectly normal, okay? And that's just, that's going to happen as sample size increases. We're going to get reduced sampling error, and we're going to get a more normal distribution in our sample. So big sample sizes are great. So sampling error, again, is just estimated from the size of the sample and the variance in the sample. The way we do that is we actually calculate a value, and that's called standard error. So standard error is an estimate of the average amount of sampling error. And here's the formula for that. This is a really important formula going forward for inferential statistics. It will be repeated over and over. Standard error is simply the standard deviation in the sample divided by the square root of n. So again, you can see the influences on sampling error and standard error right there in the formula, right? As I said, as sample size increases, standard error should decrease, right? So sample size, n, is there in the denominator. So if that goes really large, then standard error's going to go really low, right? And standard deviation in the sample should reflect standard deviation in the population. So as that goes up, standard error will go up. So to wrap up this segment, the important concepts and topics were this idea of random and representative sampling. Again, I used the color wheel illustration to demonstrate that and how we can apply it to samples and the discrepancy between samples and populations, which is this idea of sampling error. And then I showed you the formula for standard error, which is the average amount of sampling error.